Okay, in this section we're going to look at an application from physics and use our definite integral to define what's called work. Work in physics is the force times the distance, and we're going to use these two systems. In the English system, the force is going to be measured in pounds, so the work would be measured in foot-pounds. In the metric system, the force would be newtons, so the work would be newton meters or joules. And the idea is pretty simple, really. Suppose you're moving an object from, say, A to B. And let's suppose the force acting on that object is a continuous function. How would you compute the work in moving the object from A to B? Well, if it's a continuous function and you subdivide the region into these small subintervals, then the force is essentially constant on each of the subintervals. So the force needed to move the object is going to be f of x sub I star, where x sub I star could be any value of x in that subinterval. So the work done in moving the object across that subinterval would be the force required times the length of the interval. So the work across the ith interval would be f of x sub I star times delta x. And if you add all those up and take the limit as n goes to infinity, this is how we define the work. It's the integral from a to b of the force function dx. Such is the case with Hooke's law, where the force function is kx. The idea is, suppose you have the natural length of a spring and you're trying to figure out the work done in stretching it out to some value here, x equals b. What you would do is compute the work done, stretching it across each subinterval, add that work, and then take the limit as n goes to infinity to get the definite integral. So the force required to move it across this ith subinterval, where it's essentially constant. So it'd be k times x sub I star, where x sub I star is any x in this subinterval. So the work done in moving the spring across that subinterval would be the force times the distance delta x. So when you add these up and take the limit as n goes to infinity, the work done stretching it from the equilibrium position, which we'll call 0, out here to some value b, would be the integral from 0 to b of kx dx. So let's look at this example here. Force of 20 newtons is required to hold a spring that has been stretched from its natural length of 30 centimeters, which would be 0.3 meters, right, to a length of 40 centimeters. Now, think of this as 0. 30 centimeters is 0, so this would be 0.1 meters. And the question is, how much work is done in stretching the spring from 0 meters to 0.2 meters? That's how we're going to look at this. So we first have to find the value of k. Use the fact that to stretch the spring 0.1 meters past its equilibrium position requires 20 newtons. So k equals 200. So to find the work done, all we have to do is integrate from 0 to 0.2 of kx dx, and when you do that, you end up with 4 joules. Okay, we're going to change gears a bit here. Suppose you have a 50-foot rope that weighs 0.2 pounds per foot and it's hanging over a tall building. Find the work done in pulling the rope over the top of the building. I'm going to call 0 up on top, and I'm going to call 50 the bottom of the rope, okay? So what I'm going to do is take the rope and divide it up, and first of all figure out the weight of the rope. If you partition the rope into these subintervals, each with length delta x, then if the rope weighs 0.2 pounds per foot and you have delta x feet, then 0.2 delta x is actually the weight of the rope. So in terms of the work done, since this is 0, if this is x sub I star, the distance that it has to go would be x sub I star, wouldn't it? So 0.2 x sub I star delta x is the work done in pulling that piece of the rope up. So then all you have to do is add all those up and take the limit as n goes to infinity. We're adding these up from 0 to 50, and the function would be 0.2x dx. That turns out to be 250 foot-pounds. Now let's put a 10-pound weight on the bottom of that rope now, and ask ourselves how much work is done in moving this 10-pound weight up the top of the building. Well, the work done is actually the work in pulling the rope plus the work in pulling the weight. We've already computed the work of the rope. So what would be the work of the weight? Well, this is actually much easier than you might think. It's just a 10-pound weight that moves 50 feet So the answer is going to be 500 foot-pounds. Here's how you would do it with calculus, though. You would say, okay, suppose we have this 10-pound weight and we're moving it through the I subinterval. The work done there would be the weight times the distance, so it would be 10 delta x. That's the work done in moving the weight past that subinterval. You add them up, take the limit as n goes to infinity, and sure enough you do get the work, and pulling the weight up to the top would be 500 foot-pounds. So the answer to the question is, what is the total work? It's the work of the rope plus the work of pulling the weight, so you end up with 750 foot-pounds. Okay, the third type of problem I want to look at involves water. Again, we have to go back to the English and metric systems here for just a minute. Volume of water is going to be cubic feet in English, cubic meters in metric. Density of water, 62.5 pounds per cubic foot in English, 1,000 kilograms per cubic meter in metric. We also have to multiply by G if we're in the metric system. So let's look at this example here. Suppose I have a rectangular tank, and it measures 3 meters by 5 meters, and it's half full of water. And the question is, how much work is done in moving up all this water out over the top of the tank? So we first of all have to figure out what is the volume of that slab. The slab would be 3 times 5 times delta x, which would be the thickness of the slab. Then what is the weight? That's what F sub I is. That's the weight of the slab. You multiply the volume times the density of water. That'll tell you the mass of the slab, and then you multiply by G, and so that'll be the number of newtons. So when you multiply by 9.8 and 1,000, you get 147,000 newtons. Now, how far does that slab have to go? Well, in this coordinate system, I have 0 on the bottom and 8 on top. So if this is x sub I star, how far does it have to go? Why, it's going to be 8 minus x sub I star. X sub I or x sub I star doesn't make a difference. Anyway, so then when you add these up and take the limit, you get the definite integral. Now notice, I'm only adding these up from 0 to 4. If it were full of water, then I would add them up from 0 to 8. But since it's only half full, I am only adding these subs up from 0 to 4. And when you compute that, you should get 3.5 times 10 to the 6 joules. Okay, let's do one more. Okay, let's do one more here. On this one, suppose we have a tank that's 20 feet long, and the sides are equilateral triangles, 4 foot on each sides here, each of the ends. And so the question is, if the tank is full of water, how much work is done pumping all the water out over the top of the tank? First of all, we've got to figure out the height of the tank. The height of the tank is going to be, if you just use the Pythagorean theorem, it's not too hard. If this is 2 and this is 4, the height becomes the square root of 16 minus 4, which is square root of 12. So the height of the tank is 2 times the square root of 3. And anyway, also, the volume of the slab is going to be, the volume of this little slab here is going to be 20, which is the length. If this distance is x, then this distance is x2, so it would be 2x times delta y. What we need to do, though, is we're going to have to get this just in terms of y. And the way you do that is with similar triangles. You notice from this picture here that x is to y as 2 is to 2 radical 3. So you get this. And then when you solve for x, you get x equals y over square root of 3. So anyway, when you go back to the formula for the volume, then you replace 2x then would be 2y over square root of 3. So you get then the way you convert from volume to weight, since we're talking about the English system, you multiply by 62.5. So you get this. Now, how far does that slab have to move? With my coordinate system, here I have 0 on the bottom and 2 radical 3 on top. So if this is your height, it would have to move 2 radical 3 minus y to get to the top. That would be the distance. Anyway, when you add those up and take the limit as n goes to infinity, you get this, and then when you integrate this at the very end, I get a 10,000 foot-pounds. Okay, we'll see you later. Bye-bye.